Yes.
Okay, we're recording live. This is the January 10th, 2023 meeting of the Boston Mineral Club. Let me share my screen.
You can make it a little loud.
Bigger.
No.
Okay, is everybody seeing that?
No, it's gone.
No.
You're not seeing it. Okay,
Just the people.
just the people. Let me go back and see if I can get it to share my screen. Oh, it's turned off for some reason. Okay, share that screen. When I say share, I meant share. Okay, are we working
Can
now?
you make it larger? Can you make it larger?
Yes.
It's full screen. Is that everybody seeing the full screen?
Well, it's sort
Yes, we
of.
can.
Yeah, it's good enough.
Plug it in.
Mine's not full screen. It's 92.
Pretty
Yeah,
full
that's
on my screen.
There's probably some
You
issues
might
with
be able
different.
to enlarge it on your own device, you know, just stretch it on the screen.
Yeah, some people have slightly different aspect ratios on their screen, and it might be affecting how much you see. Anyway, I'm going to start here. That's just the teaser for the meeting. This is kind of where I plan on going with the talk tonight, the talks and the introduction. I'm going to do the COVID update. Obviously, that's the reason we're doing this virtual rather than live. I have one coolest thing this month that I'm going to share. I'm going to reprise the Treasurer's Report, which is an end-of-year report that was at the end of October. We saw it in November, but I'll review it again for those who might have missed it. We're going to spend a minute giving Carl a chance to talk about the web update so he can give us all a sense of where we're at and how it's working.
No.
We'll then look at the calendar and some other business. And then finally, I'm going to give the talk and we can finish with the raffle. Okay, the Boston wastewater, as I mentioned, we're seeing a winter wave. It's not quite Omicron in scale, but it's certainly bigger than I'm comfortable with. And so I just pulled the trigger and decided to have this meeting be virtual. This is from the South Boston water stream measurements. You can see that the height of that chart, and particularly some of the data points that show up, haven't been seen except during the Omicron spike. So I just figured it was safer to do it virtually since we have the capacity to do so. Can I get somebody to say they're hearing me just so that I know? It's kind of eerie when it's all quiet.
Yep.
I can hear you.
Okay, good.
Yep, we can hear you.
Super, thank you. The coolest new thing this month. This is something I popped up on the web in my feed. There was a archaeological site in Jordan where they were excavating a 9,000-year-old shrine, and as they were digging away, they discovered that these people were collecting ammonites. They had an ammonite cache. There were 150 ammonites that were gathered in a little bitty gathering area in the shrine. So as far as I know, this is one of the oldest rock collections that's been physically documented. It's 9,000 years old in Jordan. I just thought that was kind of cool to be able to come up with that kind of archaeological evidence that people have been collecting rocks for a long, long, long time. Okay, the Treasurer's Report. Again, I did this before, so I'm not going to spend a whole lot of time on it. These are the numbers from October, the sort of year-end summary that was given to me by Steve. We started the year at 32,980, and we ended the year at 37,611. So that's the kind of the big number. We gained a little over $4,000 in our bank account over the year. So it was a very, very successful year. We're above 30,000, which makes me quite comfortable. The actual checkbook balance that we can use is a little over 20,000 because a bunch of that money is tied up in scholarship accounts and printing accounts. But we're in pretty good shape, so I'm not terribly worried about our finances. Okay, I was going to let Carl take over. Should I give you the screen, Carl? Let's see if I can make Carl the presenter. Okay, where are you? There you are. Make presenter. Yes, Carl, you're it.
Oh, lovely. Thank you.
Tag, you're it.
Okay. So are you guys seeing this?
I'm seeing it. Yes.
Okay.
Nice colored picture.
Yes.
Thank you. All right. So I was just going to go through a few things. I'm not going to go through the whole site. I guess we'll just do some highlights. Yep, this is the front page. You have a join now button. So if someone is just looking to join the club, they can just hit that button and start joining right away. And then in the lower portion, these are all blog posts, and for any event we have or meeting that we have, I'm putting in a blog post, and basically it's the talk preview that Scott writes for the newsletter. I just put it in as a blog post, and they're all listed here, so you know what's coming up next and most recent events that happened.
So if somebody actually wants to write a blog that will be on the Boston Mineral Club site, would they just send something to you?
Well, if we're going to start having a blog of that type, then we would want to set up another page for that.
Okay,
the
so as
purpose
it's
of this
set up, it's
blog
not
is,
meant for that.
I'm sorry?
As it's set up, it's not meant for that. This is simply club news.
Yes.
Okay.
Yeah, but it'd be very easy to add a blog if we wanted to have the president's blog or a monthly blog with features by club members, that kind of thing. So I'll just quickly go through the membership flow. So you click on the membership item in the menu, and I wrote up this listing of all the benefits of having a membership at the BMC to make it much more promotional. What we had before was just a long, dry bunch of text that what I'm sure no one ever read. But this gives you a real good idea of what you can get if you join the club, and there's links to most of the things. So if you decide you're interested, one way to get to your membership page is through there. So on this page, you can choose how you want to pay for your membership. So a recurring payment it'll set up an automatic payment. You only have to set up this once, and year after year, it will automatically pay for your membership, and you never have to renew or anything unless you want to go in and change some information on your membership. Otherwise, it'll take care of itself forever. And then as a backup, I set up a one-time payment option, which will allow you to pay each year for your membership. And if you move away for a year and don't want to pay for a membership, you can pause your membership and then come back and pay for it again the next year. So if you want to use that method and you want to start an individual membership, you would click on the individual membership link, which takes you to this page, and it gives you 3 possible ways to pay for your membership: by check, by a credit or debit card, or using a PayPal account. And then there's a membership form that you have to fill out. So you choose your payment method, follow the instructions there, using for the most part the Pay Now button. And then once you've made your payment, you fill out your membership form and submit it, and that will send me all your information. I will check it against your existing information, make any updates needed, and then activate your account. So that's the basic flow of a one-time membership payment. If you want to make a recurring payment, you choose one of these options here: individual membership or family membership, and just follow the directions. So the events For the events, you can either use a drop down to go to individual types of events, or you can click on events, and that gives you a little explanation of what each type of event is and a link to that type of event. So if you want to pick out the information on the auction, click on auctions. It's a general page about auctions, and then you can go see the information about this past year's auction, including all the catalogs, the registration forms, the flyers, and information about donating specimens. So over in the memberships only, in the members only section, so you have to have an active paid membership to get to this. So anyone who is not paid for a renewal, even if you're a member now, you won't be able to access this directory until you pay for your renewal for 2023. So done a lot of work on this, and the new newsletters page provides instant access to the current newsletter right in your browser. It has a nice preview picture of the front page. And then below that is the full archives of all of our newsletters that we've been able to find all the way back to 1936. This was previously on the other website, but I've revamped it quite a bit and cleaned up the look of it, and it's very easy to update now. And then another feature this was previously on the old website, but at some point it was lost in one of the updates. We have a whole set of materials that are club-only materials, some of which we have exclusive permission to feature on our site for members. And so I've created a way to access all of these materials in the drop-down menu setup, divided up by topic, region, and that sort of thing. So those are just a few of the features of the new site, and hopefully people will want to poke around in there and discover all the hidden treasures. If anyone has any specific questions right now, I'd be happy to answer them.
Any questions for Carl?
There might be one in the chat. Let's see.
Yeah,
Oh,
if somebody else could be watching the chat, I can't be doing that while I'm running the meeting. So
Okay.
somebody will have to take that on.
Yeah.
Yeah,
I had a question.
Okay, go for it.
Carl.
Yes. Yeah.
I had a question. Are you the only one that has access to posting on the site?
At the moment, actually, Martin Galise also has a admin account, but I can set up different levels of permission for different people. So it's very easy to add.
I'm just wondering, yeah, I'm just wondering how, new material gets added, and if you are kind of responsible for keeping it all up to date, because that can be an onerous task.
I think just for now, I mean, it's good that so Martin has access to it. So if some emergency came up, he could definitely handle it. For now, I'm gonna control that whole thing, and a bunch more tweaks that need to be made. But in the meantime, I do plan on writing up documentation that will allow anyone, such as board members, etc., to post and update information on the site. And fortunately, it's a very easy and flexible system. So.
Have any other questions for Carl? If not, I'm going to take possession back.
Okay.
Good work, Carl.
Thank you, Donna.
Yeah, thank you, Carl. Looks fabulous.
Thank you.
Thank you very
Yes.
much.
Great
Yeah.
job.
Yeah, I want to throw in my thanks for doing that. That's a huge improvement in the website. Appreciate it very much. Okay, let's see if I can get back to where I was. Okay, so here we are. Let's present, share screen. Yes, that screen is the same one I wanted. Okay, but you're not giving me the right screen. Okay, it is there. Why isn't it letting me do it? Try one more time. Okay, share screen. Are people seeing that screen? The web update screen?
Yes.
Okay,
Yes, we can.
so it is working good. It's sometimes tricky to know.
Yeah.
Okay, in terms of coming events, I just threw in some eye candy on the left there. It's a beautiful cerusite that costs more than my car that I saw at Tucson back in 2019. Anyway, the upcoming events, we have my brother Dana talking about zeolites at next month's meeting. He and I were actually going to do them in the opposite order, but he discovered he had a conflict with this month, so we switched, and he's coming in February. With a little luck, we'll be back into personal meetings by March, but I can't promise that. But the March meeting, I managed to get somebody I've been trying to get for quite some time, Joe Bagley, the Boston City archaeologist. He and I have been working he's been working. I've been talking to him about the work he's doing on tracking down Native American quarry sites around Boston. Particularly, there's a bunch of them in the Blue Hills in the South Side. And he's got some really interesting stuff he's come up with about the amount and kinds of quarries, and it's surprising how many there are and how prolific some of them were. There are some fairly large quarries, so a lot of the stone tools we find related to Native Americans were quarried around the Boston area in some of these quarries. And he says he's got a lot of hand stuff to show with and share with people, so hopefully we can do that in person. I'd hate to bump that one to virtual if we can head that off. Is there anyone else have any other events or business they want to bring in?
Yeah, Scott, I just wanted to give a heads up that the micromounters of New England will be having a symposium third Saturday in June, which is the 17th of June. And the featured speaker is going to be Rod Tyson talking on Rapid Creek in the Yukon. So there will be a virtual element to that if folks want to log on just to see the talk.
Excellent.
I'll give you a flyer on it for the club once that's finalized.
Sounds good. Do we have any other events or business?
Scott, I thought I'd mentioned Bart Wagner has, I guess, effectively resigned as membership coordinator. So I'm going to be serving as interim coordinator since I'm handling all the membership information anyway for the website.
Okay, yeah, we're going to have a board meeting in the next couple of weeks, and I've got that as an agenda item on the board for the board to discuss. So we will take care of that. Sounds good. Thanks for reminding me.
Certainly.
Okay, at the end of the meeting, we're going to have a virtual raffle like we do at all of our virtual meetings, and these are the 5 specimens that Jonathan put together. Jonathan, do you want to talk about these, or do you want me to just kind of introduce them as best I can from your write-up? I'm not hearing.
Jonathan doesn't have audio.
Oh, he doesn't have audio. Okay, I'll just talk to them then. He was very gracious in the last minute with my flipping to virtual. He put together a set of 5 specimens that we can do for a raffle. As you can see, number 1 is an agate slice from Minas Gerais, Brazil. Beautiful gray and cream colored agate. The second one is a thumbnail of fluorictorite from Wilberforce in Ontario, a nice little individual crystal of fluorictorite. The third one is a beautiful, looks fairly gemmy in the photographs, clinozoisite from Eden Mills. That's one of the classic localities for that species. Number 4 looks like a shoral elbaite, so it might have hints of color in it from Namibia. It's not just black, or it wouldn't have the elbaite tag. And then there's a local Connecticut, East Granby, Connecticut, from the Roncari quarry. There's a quartz that has very, very pale amethyst tones to it. So it's a pale amethyst from Roncari. So we're going to be giving those away randomly at the end of the meeting. So by all means, stick around if you're interested in that. Okay, so the talk that I'm going to give is one that I've kind of been mulling for a couple of years, actually. I've long been a space fanatic, and I've been following our exploration of space since I was a kid. You know, I grew up making model rockets and such in the NASA days before we went to the moon. And I've always been interested in that. And I was particularly interested in the search for extraterrestrial intelligence. And, you know, there's sort of 2 parallel tracks. So that's largely looking for radio signals from space. And the NASA program is obviously doing hard science, looking for evidence of life on Mars and in meteorites and on the moon and other planets with probes. And so I've been very interested in that for years. But about a decade ago, there was a mineralogist who realized that the incredible events in the history of the Earth that led to life and ultimately to us being here also have a huge impact on the minerals that exist on the planet, and that the mineral heritage of a planet probably evolves much like life does. And I'm going to talk about some of that, not specifically in the exact format that the authors did, and I'll mention them later in the talk. But I'm going to kind of walk through some of the parallels I see between the search for life in the universe and the evolution of the Earth, and how that relates to minerals and the minerals that we end up having available for us to collect. So if I wander into some technical stuff, don't worry, that part will be short, and I'll get back to pretty pictures of minerals and some other interesting stuff at the end. But there's a little bit of technical stuff in the middle that hopefully I don't lose anybody on. Okay, so the sort of overview of everything I'm going to talk about is that the Earth turns out to be a very, very unique place in the universe, as far as we can tell. Initially, the whole search for extraterrestrial intelligence that started in the 50s and 60s was anticipating that they would find evidence of intelligent life elsewhere in the universe. And as we all know, they've had no luck. And NASA was hoping to find evidence of life on other planets in our solar system. And as you probably know, they've come up a duster ever since. And in fact, most of the places we've been look incredibly barren and dead. And so the question is, where does that lead us, and what does it tell us about the special conditions that led to where we are today on the Earth? And then when you get into that whole train of thought, you start to realize that there's actually a co-evolution of minerals and life on the planet. It turns out that the unusual and diverse minerals that we see on the Earth were probably a big part of why life was able to form here. And inversely, once life forms, life has drastic impacts on the diversity of minerals. So the two of them feed together in a positive feedback loop to create the enormous variety of minerals that we have available to collect here on this planet. And I think in the end, certainly I ended up with a new appreciation of just how precious the planet we live on is. And hopefully I'll share some of that with you as I go through this. Again, the search for life in the universe, I've been a big fan. I was a student with Heidi Hamel, who's the gal who ran into NASA with the pictures of the asteroids crashing into Jupiter. She's a fairly famous astronomer. And so I've been following astronomy since I was a student, even though I'm a geologist. But NASA has been doing enormous amounts of looking for all kinds of things, just trying to understand the nature of the universe. But particularly, they have an arm of their effort that's looking for evidence of life in the universe. And of course, we went to the moon and discovered that it's an incredibly dry and barren place. We've now been to Mars. We know that Mars actually had water. There's beautiful evidence of deltas and standing water early in the history of the planet. But it does not look like life ever evolved there. And I'll talk a little bit about the recent evidence we've found that suggests that even though there was water, it was probably a very toxic place that is not suitable for life to have evolved. And then, of course, we've been sending probes to various planets and to asteroids. And this year, we're about to have a sampling mission come back from one of the asteroids. So I anticipate we're going to learn a whole lot more about how the universe formed, or at least our solar system formed, in the near future as we get those incredibly pristine asteroid samples back. Anyway, in parallel to all the cool science that NASA was doing, we had the whole SETI group, which is kind of a softer science. These are the folks who are searching the skies, looking for any evidence of organized radio transmissions from outer space. And to date, they have had no luck. And just a couple of years ago, some of you have probably seen the collapse and final destruction of the Arecibo radar dish, the big one that filled a whole mountainside. That's now dead and non-active. It's slowly collapsing into the jungle again. But I think that's indicative of where SETI has gone. They've realized that there probably isn't detectable intelligence out there, but there are still people trying, and I don't blame them. It's an interesting question, and it would be wonderful if somebody could actually find meaningful signals of intelligence. But the search is starting to look more and more frighteningly dim that we'll ever be able to do that. And for those of you who are at all interested in the SETI equation, the SETI effort, the Drake equation is something that was created way back in 1961 at the early parts of this, the first big conference about looking for extraterrestrial intelligence. And they came up with this formula down at the bottom, which was basically an attempt to sort of schematically list the likely probability that we'll ever see anything coming from an extraterrestrial intelligence somewhere out there, some extraterrestrial civilization. So of course they take how frequently do stars form, how many of those have planets, how many of those planets potentially could support life, what fraction of those probably do develop life, what fraction of those develop intelligent life, what fraction of those would release detectable signs into space, and then the length of time they would be releasing those. So they came up with this sort of conceptual formula to try and estimate the odds. And back in 1961, they estimated the best they could in those equations to being somewhere between 1,000 and 100 million civilizations in our Milky Way alone that should be capable of communicating with us while we're listening. I think that ended up being proven to be very, very optimistic. And it turns out it's a classic case of unknown unknowns. It turns out there's an awful lot of things that led to us being here that are part of the unique history of the evolution of the Earth that were not figured into this equation. The biggest one, I think, is that they used the number of planets that were in what's called the habitable zone, which is defined as the distance from a star where liquid water is possible. They just arbitrarily decided that the odds were probably about 1 that any planet with water would evolve life, because obviously it happened here, so any wet planet's going to evolve life. And then they assumed that if life evolved, it would develop intelligent life. So all of those were given almost a factor of 1. We now, the more we think about it, the more we realize those are probably far, far, far below 1. So the odds are actually getting quite slim with our most recent understanding. But we're still looking, and of course NASA is still exploring for other reasons as well. And this is a recent image I almost used as a coolest things image, but I found that other one to use. This is actually an image from the James Webb Space Telescope. You probably heard about it in the news. It's the most incredibly powerful telescope we've ever built. Put it up in space. It's an enormous big gold mirror that's shielded from the sun. It gets to look out into deep space and can see further than any telescope has seen before. And this is actually a pretty spectacular image that they published about a month ago. This is one of the first experiments they did, which was to go and look at what was considered a dark patch in the sky. It's an area that previous telescopes hadn't seen much in. So they thought this would be a good place to just see how far we can look. And when they tuned in and they zoomed all the way out, and just to back up a little bit, the James Webb Telescope actually has an infrared detector, because the further away you get, given the red shift that we know about in galaxies, the further away, the more you shifted to the red end of the spectrum. They're now starting to look so far out into the galaxy that they're expecting normal visible light to be extended all the way into the infrared. So it's right out of the visible spectrum from the Doppler shift. It's so far away and moving so fast away from us. So a lot of these are detectable only in infrared. They don't give any visible light. But this is a star field. There's only about 5 stars from our Milky Way that show up in here. They're the ones with the little pointy things jumping out from them. Those are local bright points of light from stars in our Milky Way. But all of those other things are galaxies that they found when they looked into this dark patch of space where previous telescopes had not seen much of anything. And it's basically telling you that space is just chock full of galaxies. I mean, there's lots and lots and lots and lots of stars out there. So the odds that there's life out there somewhere is probably actually improved by views like this, to realize just how many stars there are in the universe, in the larger universe. But unfortunately, the problem is not does life exist, but does life exist at a distance where we can physically detect it? And that's a very, very different question. That's the SETI question. And unfortunately, this doesn't help us with that. But it does open our eyes to just how vast the universe is. Okay, so coming back to the reasons, some of the reasons why the SETI experiment has exquisitely failed. We've not found any evidence of communication from extraterrestrial intelligence to date. And as I mentioned, there are a bunch of unknown unknowns that we've now discovered ought to be plugged into that equation. There are things that have happened on the Earth that don't happen to a typical planet or a typical solar system. And I just listed some of the things that scientists have flagged that might make us a little more unique than we had previously thought. We're a relatively low density solar system compared to the number of planets, and particularly big planets, that we're now detecting in some of these extra these star systems we're looking at now and detecting planets in through eclipses and other things. It turns out planets are a lot more common than we thought, and really, really big planets are a lot more common than we thought. We have a relatively low density solar system compared to the average galaxy out there, or the average solar system out there. And it may be that having a few small planets in the habitable zone where liquid water is possible, and having a couple of really big planets further out, creates a sort of what they call a guard planet scenario, where comets and asteroids that are flying around the solar system largely get caught and absorbed by those big planets and protect this inner zone from massive bombardment. And so it may be that the Earth was somewhat uniquely shielded from major disastrous events, from collisions through most of its history. Another thing we've discovered in looking at other stars is that most stars are not as stable as our sun. Most stars give off periodic bursts of high intensity radiation, and those things could easily just bake a planet if it happened to be in the wrong direction when an eruption like that happens. So we may be in a very fortunate situation that we're in a middling size, relatively stable star that hasn't fried us in our seats, as it were. Curiously, the Earth has an anomalous amount of water, and I've yet to see a good explanation for why that is, and I'll talk a little bit more about that as I go. But obviously, the presence of large amounts of water is something that would obviously make a big difference to the ability to create life. The Earth is a highly segregated planet. We have a very large iron core, solid inner core, liquid outer core, mantle. Upper and lower mantles seem to be segregated and slightly chemically differentiated. Obviously, there's a core, there's an ocean, there's an atmosphere. So the planet has differentiated quite extremely, and it looks like it's done so more than some of the other planets we've looked at. And so it's possible that something about the Earth caused it to segregate more than a typical planet might. And one of the reasons is this next unit, which I stole a little picture off the web for, is the idea that now exists, the dominant theory for the creation of our moon, which is an anomalously large, anomalously close moon by the standards of most other planets. And of course, that creates tides and all kinds of interesting things that might influence the ability to create life. It turns out we now believe that there was actually a collision of a Mars-scale planetoid with the early Earth a few 100 million years after formation, and it basically liquefied the entire planet and spalled off the moon as a blob of molten material from the Earth's mantle. And it was only after it cooled that somehow comets with water came pouring in to create the oceans and give us our current situation. But the chemistry of the moon and the Earth and asteroids and meteoritic material, all of that tells us that the moon and the Earth probably formed as a single body or a single collision. And there's lots of good evidence now that's supporting that. So that's something that's extremely unusual. That was not even on anyone's radar, if you will, no pun intended, when the initial SETI efforts were being done. People were assuming anything that's in the position where the Earth is in terms of being in the liquid water zone ought to have a simple history and have life. It's now looking like the Earth had a very, very unusual history, and that may well have had something to do with the ability to generate life here. Of course, the Earth has a tilt. It's tilted 20 some odd degrees to the plane of the solar system. So as we go around the sun, we get fairly significant seasons. And of course, the ability to turn water from gas to liquid back into ice and back again, that energy transfer and the heating and cooling that happens during the seasons may well be a huge part of what allowed life to form in some exotic environment somewhere on the early Earth. Another huge thing that happens on the Earth that we haven't found good examples of on any other planet is plate tectonics. Our mantle is convecting in the solid state and moving the surface plates around. And that has a huge impact on the thermal state of the Earth. It has a huge impact on the geothermal gradients that exist in different parts of the Earth. We get very, very hot zones where the plates are coming apart. We get very, very cold zones where the plates are coming together. And those create very special environments that may have fed some of the energy transfers that could lead to the creation of early life. And then another thing, the last one I want to mention, is this idea of a snowball Earth. And I think I've mentioned this before in a meeting, but there was a time around 650 million years ago when basically all of the continents on our planet froze over with continental ice sheets, and there was no exposed land to speak of. And all of those ice sheets pretty much extended out into the ocean. We have good examples of those here in the Boston area. There's actually exposures of tillites down at Squantum Head. A beautiful, beautiful example of that that's found down there. So we have a local example of about a 650 million year old glacial deposit that was probably from that snowball Earth period. And right now it's just a correlation, but that timing is curiously related to the time when life exploded into complex forms, just into the Precambrian Cambrian boundary. So there's a spooky correlation between the time when the Earth froze solid and then melted, and when life exploded into more complex forms during the Phanerozoic. So it's entirely possible that something about that deep freeze of the Earth led to the evolution of more advanced life forms on the planet. So all of those things are unknown unknowns that we've discovered since the time of the early SETI equations. And then the more important thing, I think, is actually this last little bit. It turns out that detection is a lot more difficult than we initially thought. Initially, the thought was we'll just look out there and we'll point it star after star after star and see if we can pick up radio signals. But it turns out, 1 over r squared, basic physics, the strength of a signal dies off with distance. And people have done the math to figure that with our own detection technology and the kinds of radio waves that we were sending out during the early radio and TV years, that we would not be able to detect ourselves more than about a light year away. And of course, the nearest planet is much further away than that. So we wouldn't even be able to detect a civilization like our own at Proxima Centauri, never mind, the hundreds of thousands or hundreds of millions of stars you'd have to sample to make the Drake equation work. And people have done the math and realized that the equation was a little goofy too, that we need to be looking at the time overlap between when they're sending signals and when we're listening. And that creates an additional component that drops the likelihood. So anyway, there's lots of reasons we now believe that the odds of us detecting another intelligent species is vanishingly small. But that's not to say it was not worth doing. We've obviously learned an awful lot in the process. Obviously, the search for extraterrestrial intelligence caused us to look into a lot of scientific questions that ended up giving us interesting information. This whole idea of the collisional moon formation, that's one that a lot of people might not have been thinking about or looking too hard at if it hadn't been for trying to figure out why the Earth is a little different from everybody else. And what does all this have to do with minerals is the key question for talk, obviously, for the Mineral Club. It turns out that a lot of these unique characters in the history of the Earth also have implications for the mineral diversity that occurs on the planet. And so if you have this collisional moon formation, it assists in the differentiation of the layers in the Earth. If you create an iron core with a magnetic dynamo, it creates the ability for magnetic fields to deflect the solar wind so that we're not cooked by the occasional solar flare that we get radio interference from. Other planets don't seem to have that, and those are pretty much barren because whatever water they had has been blown off into space by the solar wind. As I said, I don't know why it is. I haven't seen a good explanation, but we have enormous amounts of water on this planet. And as a result, the water is relatively non-salty. I mean, we obviously think of it as salty, but it's not a brine in the sense that we now think the water on Mars was. The rovers that are sampling Mars right now have real strong evidence that there was water, standing water on Mars. But from the minerals that have precipitated out of it, it was probably an incredibly salty brine that would have been very inhospitable to life. And it probably had a fairly thin atmosphere, so they probably were subjected to intense radiation. So there's lots of reasons to think that we may not find actual evidence of life, even single-celled life on Mars. Again, I talked about plate tectonics. You can create very hot and very cold environments. So in terms of minerals, you now have very different environments for metamorphism and thermal alteration. A whole bunch of minerals become possible when you start cycling elements in and out of the mantle like plate tectonics do. The whole idea of volcanic arcs that we have that create a lot of the minerals that we love on this planet probably would not have been possible without active plate tectonics. There's some suspicion from radar work on Venus that Venus may have had plate tectonics early in its history, but the evidence is that it's long since dormant and isn't active today. So as far as we know, we're the only planet in our solar system that has active plate tectonics. And then, of course, the last factor is the evolution of life itself. Once life gets going, it has a huge impact on the planet. Has a huge impact on the planet and the minerals that can form on the planet. And in particular, once life gets going, life is a non-equilibrium process. So you very quickly you create a non-equilibrium atmosphere. We have oxygen, free oxygen in our atmosphere, and that creates a fundamentally different environment for the creation of minerals. And a lot of the minerals that we've grown to know and love would only exist in that kind of an oxygen atmosphere. So life itself has greatly increased the mineral diversity of the Earth. So I mentioned that this was all from a paper. This is Hazen and others, 2008, called Mineral Evolution in the American Mineralogist. And they went through and they estimated the number of actual mineral species which existed at different times during our history. And this is kind of a summary chart of what they think the history was. If you go back to the Big Bang, it was all protons and neutrons. There were no solids, so there were no minerals for milliseconds after the Big Bang. But as the universe expanded enough to cool down to create atoms, you very quickly probably started to create a smattering of various liquids and solids that started making planets. The first stars probably didn't have a lot to work with. They were mostly hydrogen and helium. It wasn't until you had a few big stars start cranking out heavier elements that you're likely to get anything like a rocky planet to form. So it's not entirely clear what the first couple of star lives of the universe would have in store in terms of the number of minerals. But there's been some work on meteorites in what they call pre-solar grains. It turns out in the dusty matrix of chondrite meteorites, which are the most primitive form of meteorites we know, they've actually been able to identify about a dozen minerals that seem to have predated the solar system. So these are solid crystalline substances in microscopic little specks that they found in the matrix of these early primitive meteorites. But again, only about a dozen minerals, the common sort of pyroxene, olivine, some oddball things. We'll talk about what those are in a minute. We know from theory now that at some point the hydrogen and helium collapses into the sun. The vast majority of the material in our solar system collapses into the sun. The sun gets dense and ignites, melts all the dust and debris that's out in the area, and you get these things called chondrules, which are essentially melt drops. that get spit out into the atmosphere, into the solar system, and they crystallize in these little spheres, and those things collect into meteorites, and eventually they form into planetesimals. When they get big enough to form planetesimals, you start to get thermal heating of the interior. So you now get a primitive form of metamorphism. So you start to actually create new minerals from that initial metamorphism. And they think that planetesimals probably had on the order of 250 different minerals available to them based on that simple heating of chondrule compositions. Of course, then we have early melting of most planets. We know on our moon we had this enormous big impact that created a very large moon. And so you get these various systematic differentiation events, which probably led to an increase of about a factor of 2 in the number of minerals that are available to form. Again, they're mostly compositions that are just slightly different from mantle composition, because you haven't done a whole lot of very strong differentiation yet in most planets. But we know by the time you get into the Precambrian, we have what's called the greenstone belt period in the Precambrian. We start to get things that look like modern melts and igneous rocks that we would know of. Unfortunately, the paper used the term granitoids and pegmatites, but they're not granitoids and pegmatites as we mineral collectors would know them. There's no granite per se. There are no pegmatites like we know granite pegmatites. These are simply igneous rocks with last coarse-grained residuals that formed. They're mostly more mafic looking things, sort of gabbroic, anorthosite kinds of things. But you do start to make melts, and you do start to make early melts, preferential crystallization. So those start creating some additional crystals that could form. So you're now up to about 1,000 potential minerals. At some point, plate tectonics kicks in, and then things really start rolling because you're now creating anomalously hot and anomalously cold places. And so you get a much more diverse range of metamorphic conditions that could create minerals. So you add a half again the number of minerals that probably existed just from plate tectonics alone. Then there's an event called the Great Oxygenation. Many of you have probably heard about it. About 1.8 billion years ago, organisms created enough CO2 by consuming oxygen and consuming CO2 and other things. They spit out oxygen and they oxygenated the atmosphere. So you now have free oxygen. Since that time, we've had a very, very different disequilibrium atmosphere from the planet. And so you have an oxidation zone at the surface, and that oxidation zone creates enormous numbers of minerals. And I'll show some pictures of those in a bit. But so now that you've got life forming, that changes everything dramatically. So you almost triple the number of minerals that are available just by creating a non-equilibrium atmosphere. And then, of course, life itself creates minerals. You get living organisms actually spitting out minerals. Everyone's familiar with opal or calcium carbonate or those kinds of things, aragonite. There are lots of actual biominerals that are formed. And it turns out there's a lot of exotic ones that happen when you look in places like the oxidation zones of mines. There's lots of bacterial degradation that goes on. So it's actual life that's chewing away at the rocks and spitting out new minerals. And we've identified well over 1,000 biologically created minerals that have added to that list. So at this point, as opposed to early in the history of the atmosphere of the solar system, when we had a handful of minerals, we've now got over 5,000 known minerals that exist on our planet. And so it's an interesting concept that the mineral heritage of our Earth has evolved along with the planet and along with life. It's a fascinating concept, and I think it has the ring of truth in my book. So I'm going to step back a little bit and talk about some of the stages that happen in this sequence, because it turns out they actually explain a lot about why we see the minerals we do on the Earth. And it starts by going all the way back to shortly after the Big Bang. When you start making stars, you make yellow stars as material starts to accumulate. Those yellow stars are dominantly hydrogen, which is fusing into helium. That's what creates the energy that lights our sun, that lights most yellow stars. So you've only got hydrogen and helium. There are no minerals involved at this point. It turns out only when you get a planet that's big enough and massive enough does it expand and run out of helium fusion and start fusing bigger elements like carbon, oxygen, neon, and magnesium. And similarly, when that runs out, unless you get to red supergiant size, you don't make anything bigger than that. But at that point, you start what they call carbon burning, and you can start adding additional, massive fusions to make bigger and bigger elements. So here come the ones we're used to: the sodium, silicon, sulfur, calcium, some of the things we start to recognize as fairly common in the minerals that we collect. And of course, if you get to the really, really big stars, you start to be able to create things as big as iron and nickel, which turn out to have very, very stable atomic configurations. Anything bigger than iron or nickel, it turns out you need to have a supernova explosion to create them, and the multiple neutron captures to create all kinds of bizarre, larger elements. But those things simply don't exist in the early universe. They have to be created by star processes. And of course, the Earth and our sun are a little over 4.5 billion years old. Our universe is thought to be 13.7 billion years old. So we're several star cycles into the evolution of our universe. And our solar system inherited all of the accumulated debris from at least two cycles of star formation and destruction before us. So a lot of these heavier elements already existed in the soup that made up our solar system. And that's a fairly important thing to recognize in terms of understanding the mineral heritage on our planet. And in terms of the minerals we expect, this is kind of the technical down in the weeds diagram that I threw in. This is a chart of stable and semi-stable isotopes of the elements that we know of. So just to kind of walk through the details, this is across the bottom axis is the number of protons. So the columns are different elements. So you see hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, etc. So every time you add one proton, you define it as a new element. The vertical axis is the number of neutrons that are in the atom's core. And so if you look down in the far lower left of the diagram, down here, you can see at one proton and no neutrons, you have a naked hydrogen atom. That's the normal common hydrogen atom. And you see I put a little red star, a red dot, because that's a fairly common thing in the early solar system. If that attracts a proton, you get a stable deuterium version of hydrogen. And you can see in black, these are the stable, meaning they'll last as long as the solar system does. And in blue, these are ones that, they last more than a few minutes anyway. So they last long enough to interact with something else. But you'll see as you're down in this lower corner, starting with hydrogen, you have a continuous black trail of stable elements that will lead you all the way up to helium-4, which is a very, very stable atomic configuration. But to get beyond that, you can't do anything with adding a proton or a neutron, because you see you go off into the white space. So if you added a proton or a neutron to helium-4, you end up with an unstable configuration. It just spits the proton or neutron back out. So you end up with this gulf that's hard to cross. And it's only when stars get big enough that they manage to jump that gap. And it turns out that if you smash a whole bunch of heliums together in rapid succession, you can jump over, you can see boron, which is unstable, but you can get all the way to neutron if you do two of them quickly. And so you're now into a separate track of black stable field. You can see this sort of zigzag pattern that goes up 3 and over 3, up 3 and over 3 for a long, long way. That's the chain of stable atoms that can be created just by fusing heliums onto pre-existing atoms. So you can see they jump by 2. So you go from carbon to oxygen to neon to magnesium to silicon to sulfur to argon to calcium, and eventually all the way up to iron and nickel if you follow that trail, but you start to get less stable isotopes as you get up toward the top. But you'll start to recognize that all of the really, really common elements are in that chain. They're these helium additions in solar fusion that create those main elements that we're used to in the mineral formulas that we're familiar with. And all of the other weird stuff that's up on the chart, you'll see there's a thin line that runs up diagonally on the chart. That's the line where the number of protons and neutrons are the same. It turns out when you get to bigger and bigger elements, it's no longer stable to have the same number of protons and neutrons. You need extra neutrons to hold all those protons together. All those plus charges want to repel each other. They need neutrons to glue them together. So you reach this point beyond about calcium where you can't just fuse helium atoms anymore to make stable elements. You've now got to start with massive red supergiant conditions to have all of these neutron bombardments making other elements that go above that. You can see you don't have to jump very far up till you get into another one of these cascading strings of black stable elements that run all the way up to iron and nickel. And so there's these strings of events that define different types of stars. And we've had obviously all of these in the history of our Earth, the history of our solar system, because all of these elements that we see running all the way up to, even beyond into uranium and some of the other elements that are quite rare, those must have happened in a supermassive supernova event. They must have been created. And we know that they exist in our solar system because we've looked at the spectrum of the sun, and we can analyze the waves that are coming at us and tell what atoms are being excited and de-excited to create those waves. And so we can actually determine the rough composition of the sun. And this is a plot that's been created by various people. I just pulled a copy of this off the web. These are the abundances of elements in our solar system, basically the elements in the sun, which is the vast majority of the mass in our solar system. So this is a good proxy for what the material we had to work with when we started our solar system was. So you can see here, hydrogen and helium, they're way more common than everything else. This is a log scale, so every tick mark is a factor of 10. So there's 1/10 as much helium. There's less than 1/10 as much of that of anything else, probably 1/100th of that of anything else. So most of the universe is most of our solar system is hydrogen and helium. But in terms of, and then you can see this big drop. That's that gap that you can't get over because helium is so stable. And it's only when you jump that gap and you get to carbon, oxygen, magnesium, silicon, sulfur, calcium, this string of elements, that's where all of the rock forming mineral elements come from, is that stellar factory that's creating bigger and bigger elements out of helium fusion and then carbon burning. And so you recognize the elements that make up most of the minerals we're familiar with. So carbon, oxygen, magnesium, silicon, calcium, sodium, aluminum, iron. Those are the dominant elements that make up minerals on the planet. And if you look at the ones I've got in blue, these are the lighter elements that, unless they bond with something bigger, end up either in the ocean or in the atmosphere. So hydrogen, helium, carbon dioxide, N2, O2, neon, which is an inert gas, all of those end up in the atmosphere or in the ocean unless they bond with something bigger. But all of these other elements, the ones in black, you can see those are the ones that make up the vast majority of the minerals that we're used to. Curiously, these ones down here, these unusual ones, the boron, beryllium, and lithium, they do exist in very small quantities, but and they're usually made by cosmic ray spallation. They're not made by stellar evolution. They're actually made by decay of bigger things. They're little fragments that break off of radioactive decays of larger elements. But those get purified in the granite making process. So things like boron and beryllium and lithium, we see them in the pegmatites that we're used to because they get so purified that they actually come up to the point where there's enough of them to make minerals. But one of the things that's interesting on this chart, you'll see that iron is way up high compared to the long run trend. It turns out that iron is a particularly stable atomic configuration. So there's a little plateau that stands up. So if anything, if a star gets big enough to make iron, it makes a lot of it. And so we have a history of a star like that in our past. So going back to the early solar system, I talked about the fact that there were not a whole lot of minerals in the early solar system. This is a specimen from my collection of a chondrite meteorite. This is a find from 2001 in Morocco. You can see these little round things that look like, look the size of a pea or smaller. These are these round things called chondrules. These were actually molten rock beads in the early solar system that were floating around, crystallizing when they cooled down, and then accumulating into asteroids and planetesimals. In addition, there are some other little things that are found in here. There are things called CAIs. These are calcium aluminum inclusions. You can see these in this particular sample. They're the sort of irregular blebs in the upper left quadrant of this slice. Those are CAIs. They're unusual accumulations of calcium and aluminum and some oddball minerals, a couple of oddball minerals that come with that. But those are these CAIs that you may hear talked about in meteoritics. Occasionally you get little blebs of iron. I've only found one tiny little bleb of iron on this particular slice. And people who study all that fine-grained matrix that sits between the chondrules have discovered all of these pre-solar grains that we talked about. They found graphite, they found dust, and in that dust they found pyroxenes, olivines, calcium plagioclase, silicon carbide, perovskite, and even diamond have been found. But again, you can see you're not looking at more than about a dozen minerals that existed at this early phase in the solar system. So when the vapor that was our solar system first condensed, there were only a handful of minerals that were possible. Nothing like the diversity that we know of on the Earth today. Of course, we talked about all those various cycles. You differentiate the planet, you create metamorphism, you trigger plate tectonics. Plate tectonics is a huge one, and so I threw in this diagram. Some of you may recognize this. I made this diagram for the newsletter. This is an example of the evolution of igneous rocks. The mantle sits way over to the left. You see that ultramafic column. Typically, olivine and pyroxene are the dominant minerals in the mantle. If you start trying to get melts or differentiate mantle, you start getting mafic rocks, which we know as gabbro or basalt. In the case of the moon, we know it was slightly different there. When the moon melted at one point, you got calcium plagioclase floating to the top, creating these anorthosites that make up the highlands on the moon. But again, you're only up as far as the mafic column on this chart. You never get to the right into the intermediate or felsic rocks on planets like Mars or the moon, or moons like the moon. On Earth, though, because we're now cycling plates and we're taking and eroding, subducting, melting, reprecipitating, and going through this cycle over and over and over again, we're continuously refining the material to the right and giving more and more felsic, more and more lithophilic, if you will. They prefer to be in the crust and not the mantle. So you get more and more felsic compositions, all the way down to the familiar ones that we're used to here in New England, where you're actually making granites. So you're getting quartz, K-feldspar, sodium feldspar, muscovite, and of course the pegmatites that go along with those, which are even later refined products that have only the most extreme volatile components. So you get all the fluorine bearing and water bearing components to give you all of the exotic minerals that we love from pegmatites. So those things would not happen on any other planet that doesn't have plate tectonics. So plate tectonics is a huge part of the mineral diversity that we see on our planet. And of course, a lot of the metamorphic conditions we see on our planet are only created by plate tectonics. So it's hard to underemphasize the implications of plate tectonics for mineral diversity. Anyway, this is a popular diagram that was, this is a version of it that was produced by Haxel in 2018. This is now looking at, after all of that stuff, if we look at crustal abundances today, this is what we have. And again, you'll see that cluster in green, the rock forming elements. You see your oxygen and silicon and aluminum sitting at the top as the most abundant. So no surprise, silicates are the dominant minerals on Earth. Aluminosilicates at that. And then they're typically paired with sodium, magnesium, potassium, calcium, iron. You see the next ones below that in abundance. That's why we have most of the minerals we have today. And if you come down into the sort of lighter green, you can start to see H, because there's hydroxides and waters bonded in minerals. You got carbon and fluorine and phosphorus and sulfur and chlorine, titanium, manganese. So some other minerals that show up common but not abundant. So they show up in lots of minerals. And then, of course, everything down to the right is less abundant and has to be refined. And typically we don't see them except in ore bodies where they have been refined by geologic processes and purified. So all the coppers and zincs and nickels, all the things we would see as ore minerals, zirconium, barium, those things, and lead way over on the right, those things you have to have something like an igneous process leading to ore body generation to even get those things concentrated enough that you'd ever make minerals out of them. But that's how we got to the situation that exists on the Earth today, is through all of these various processes. So now I'm just going to jump and do the sort of summary, looking at some pretty eye candy pictures. Without oceans of water on the Earth, you wouldn't get all of the hydrated minerals that we've come to know and love. There's obviously lots of clays and things that are not as pretty, but all of the zeolites are predominantly hydrous phases. So all the stilbites, apophilites, lamentites, all the beautiful zeolite minerals that we're familiar with from India and elsewhere up in Nova Scotia, none of those would exist without the oceans of water that we have on our planet. I mentioned plate tectonics several times. These are two classic examples of minerals you would never get without plate tectonics. On the right is a sample of bonitoite from my collection from California. That's what's called a blue schist mineral. It's from an anomalously cold geotherm around a subduction zone. So minerals like bonitoite, neptunite, waukeanite, glaucophane, lawsonite, jadeite, nephrite, all of those require unusually cold geotherms to form and would not form on any planet that didn't have subduction zones. And of course, here in New England, we all love pegmatites and pegmatite minerals. This happens to be an example from China from my collection, but it's an example of a granite pegmatite. You get beautiful quartz, microcline, muscovite, garnets, and all of the associated minerals that we're used to from granite pegmatites, all of the tourmalines, all the beryls, all the spodumines, all the topazes. None of those would exist on a planet without plate tectonics. Obviously, now that you've got the great oxidation where life created a non-equilibrium atmosphere with free oxygen, we have an oxidation zone at the surface. So all of these ore bodies are slowly decomposing and creating oxides and carbonates and interesting minerals from the more pure forms that would exist in an equilibrium situation. So a lot of the really colorful, really beautiful minerals that we like to collect from ore bodies simply wouldn't exist without life making free oxygen for them to interact with the ore bodies. And similarly, life itself makes elements, makes minerals. This is a classic example from the Harvard collection. There's an amylite that they have on loan for the current display, but that's a mineral that was created by the critter itself. This ammonite deposited a shell of aragonite, which has got this beautiful iridescence for these particular shells. But a lot of calcite, a lot of aragonite, a lot of silica is all directly deposited from living organisms, dropping them out as part of their life processes. And so there's lots and lots and lots of examples that you can look at on the Earth of why the Earth is unusual. And then finally, to close, I'm going to pull out this slide just because I love it. It's the first image we had from the Apollo mission looking back at the Earth. This is the moonrise, the Earthrise over the moon. It's one of the most iconic photographs of the last half century. Or last century, I should say. And then the quote, the end of all our exploring will be to arrive where we started and know the place for the first time. I think the result of our NASA efforts and our SETI efforts and our geologic understanding from visiting other planets and studying our Earth in detail is an incredible realization of just how unique this little blue marble that we live on is. And I personally hope that in generations to come, we start to appreciate just how unique it is and not have this dream that we're going to somehow go colonize one of these barren rocks around us and create a second home. I think we should more likely think, let's find a way to make the Earth habitable and sustainable and keep it live. Anyway, so that's my talk. Are there any questions? I know I covered a lot of material.
Fantastic. I understand things now I never understood before. Thank you.
Yeah, I thought that might be the case. I certainly learned a lot in putting this together. It's a
Really
fascinating
great.
subject.
Thank you very much for that. That was very informative.
Were you ever a teacher?
I was a teacher in the sense that I earned my way through graduate school as a teaching assistant. I was never a professor per se, but I was a student teacher. I've had lots of people say I should be a teacher, but I've never been paid per se.
Amen.
Well, you're teaching us.
Well, that's the whole point. Yeah, we are an educational institution.
Fantastic. Thank you.
Any questions about the
Scott,
presentation? Yes.
Have you heard the theory that Jupiter formed more on the outer fringe of the universe and migrated more inwards, and perhaps bringing ice bearing by virtue of its gravitation, bringing ice bearing, the ice bearing outer things like in the Kuiper Belt in, and that's maybe what not only bombarded Earth, but resulted in this larger gas giant a little more inwards, where it could help defend the Earth from bombardment. And I had heard this, and I just didn't know if it had gained any traction in the scientific community. And it seems to me that would be a really unique thing that would help preserve life.
Just a couple of comments along those lines. It's fairly well established in astrophysics that planets do kind of migrate in towards the sun around which they form. There is a general decay of orbits that happens very slowly over the life cycle of a solar system. So all of the planets we know of are probably closer to the sun today than when they formed, including Jupiter, including Saturn. And it's quite possible that Jupiter was further out toward the Kuiper Belt, and it may well be that that was what was disturbing so many water-bearing comets that brought all the water to the Earth in the early days after the moon had formed, because we were probably a hot molten body that cooled down quickly, and we'd have to get water coming from somewhere. So it probably that's one explanation for why that might be, would be a Jupiter that was kicking icy comets out and crashing them into the inner solar system. Anyway, I don't know if that answers your question.
I was wondering if the presence of oxygen on the Earth would be something that would have encouraged the formation of water, or if that's a chicken before the egg kind of situation.
I think it's chicken before the egg, because we know from rocks that exist prior to that age, we have rocks going back to about 3.5 billion years old. It looks like there were oceans all the way back. So we have the same kinds of water dynamic systems creating sediments 3.5 billion years ago. So clearly there was enough water to have an ocean before the oxygenation event. So it's more likely that the oxygenation event is simply an evolutionary stage of life and not the reason we have water.
So I have a question. You've used the word life a bunch of times, and I'm wondering, in the area of study that you're talking about here, how is life actually defined? You seem to, for example, assume that water is required for life.
Obviously, we only have one example of life. All of the life we have shares DNA heritage, so they're all originally coming from some single source. They may have been others, but they went extinct. But everything that's alive today, as far as we can tell from DNA studies, came from some original parent way back in the early history of our planet. And so we are basically one example of life that has evolved over time. There's actually a whole arm of science nowadays, now that we can actually break down the genetic signature of life. People are starting to read the genetic codes and make these genetic trees to figure out how far back different linkages happen in time. And they've linked everything back together to a very small time period in the Precambrian somewhere, where the early Precambrian, where the first celled organisms must have formed. But we're basically a single life that has evolved into a variety of forms. We all share a common DNA. We all share common ancestors. If you go far enough back.
Has anyone done studies just sort of theoretical studies to decide whether or not some non-carbon based life form could develop? You know, are there similar chemical capabilities in different elements?
The concept of silicon-based life, which you see in science fiction stories going back to the 50s, the only reason that people think about silicon is it also happens to be capable of bonding with 4 oxygens, just like carbon can bond with 4 oxygens theoretically. So it has a similar kind of It can make 4 bonds, let's say. It has a similar kind of chemistry. So people argued, well, why can't you have, excuse me, I'm saying oxygen, carbon and silicon. Carbon can bond to 4 other things. Silicon can bond to 4 other things. So people have made the assumption that maybe there's a kind of life that we don't see on this planet that is based on silicon somewhere else in the universe. And I mean, that's a hypothetical that you could come up with, but nobody's been ever able to create anything that could replicate made out of silica. So it's a purely theoretical concept at this point. The big thing about life is that it's able to reproduce itself and pass on its genetic heritage. That's really kind of the definition I've seen most people use.
So there is a question from Jonathan in the chat. Can you see that, or?
I'd have to get out of my presentation. Can you read it to me?
Yep. It says, what about recent news that there may be opals on Mars?
Yes, you can make opal inorganically. You don't have to have life to make opal. Opal can form just from silica saturated water. And that's probably what you're seeing on Mars is just silica saturated water precipitating in cracks. There's no evidence that that's actually formed from life. Science is nasty in that it creates some terminology that's very, very confusing to the layman. You'll hear organic chemicals and organic chemistry being described in the chemistry that they're finding on the moon, actually on Mars. And in fact, they are finding what are technically organic molecules, but organic molecules and life are not the same thing. Organic molecules are just carbon-based, carbon, oxygen, hydrogen, sulfur-based molecules. Ring structures, chain structures, those kinds of things. Those things can form inorganically. In fact, there's the old Urey experiment from the 50s where if you put a whole bunch of carbon-based compounds together and put sparks through it, you can make amino acids without life. You can just do it from a spark in a test tube. So you can make things that look kind of like organic molecules, and they are technically organic. They're just not life-based. And so most of the organic stuff we're seeing on Mars is probably inorganically formed. So the terminology is very confusing to people who aren't sort of in the know about what organic means from a chemical standpoint.
Scott, I was also following the dating of the mineral based on zirconium oxide. It's basically uranium decay, and it looks like the earliest minerals or solid state matter on the Earth is beyond 4.2 billion years. But and that's still moving on. That's a moving target. But this is a zirconium oxide. So at that time, the oxygen must have been present as well.
No, you don't need free oxygen to make zircon. Zircon comes just from igneous processes. You can make those in granites. It's a common accessory mineral in granites. Just for people who aren't familiar with the story, the oldest documented rocks that we have on Earth, because plate tectonics is recycling the surface over and over again, we don't have rocks from the earliest Earth. The oldest ones that have not been recycled are about 3.8 billion years old. And it turns out that in those rocks, there are grains. Those are sedimentary rocks. In those rocks, there are grains that include zircons. And those zircons have been dated very carefully and found to be 4.2 billion years old. So there was an igneous rock with a zircon accessory mineral that eroded into these sediments. The igneous rock formed 4.2 billion years ago. The sediment formed 3.8 billion years ago, and it's all been preserved till today, so we can look at it and pull those dates out. So we know that there were solid rocks on the Earth at 4.2 billion. And we know that the moon event happened maybe 100 million years or so after formation. So there's only a couple of 100 million years between when we think the moon event formed and you create the oceans and you create zircon-bearing igneous rocks. So there's only about 300 million years. It's a fairly short window. So things happen pretty quickly.
The way how I understand it's a zirconium oxide, really that they are ablating teeny tiny crystals of a zirconia, and this is a zircon dioxide.
Yes, it is zirconium oxide, but you don't need free oxygen to make zirconium oxide. Oxygen's the most common element in the solid Earth, and so you can get zirconium linking with oxygen without ever going into a free oxygen atmosphere condition. Zirconium
Okay,
forms all the
understand.
time.
Yeah, thank you.
Hey Scott, question that was, I've often read where it says stars have a limit of creating elements, and it stops with iron. And I never saw a good explanation for that. But then one of your charts, maybe this is what it is that they can't produce enough heat. Is that what the reason is? And that you go to supernova after that? The only way you could produce those was with extra heat? Or is there another compounded reason and why iron is the limiting factor or the limiting element?
Can you see the chart that I brought back?
Yes.
Okay.
Yes.
Again, you can follow that line up along with all the red dots. So you can see what slapping helium or alpha particles, helium atoms into a nucleus would do. You keep jumping these red dots, and at some point you run out of stable elements. So when you get to iron and nickel, there's nowhere left to go in that most common form of element creation in stars. Anything above that on the chart or higher than that on the chart has to be created in massive red supergiants or supernova explosions. So it's another process, a much more highly energetic process than the normal star stuff. You have to literally have these incredible explosions that are orders of magnitude more energetic, which happen when giant stars collapse when they run out of fuel. And then they collapse so hard that a new form of energy explodes and they go supernova. And it's during those supernova explosions that you create everything heavier than iron. Iron is a very stable one, and it's made by regular sequence stars. Anything heavier than iron probably had to come from a supernova. It's interesting on this chart. I only showed the lower left corner. Obviously, there are lots of elements off to the right beyond this chart. You actually run up to a point where you get to about 80 on the atomic chart. Beyond 80, there are no stable elements anymore. Everything above 80 has a half-life and will decay over time. So the stability drops off very rapidly as you go off up to the right from what I've shown on this chart. When you get up above iron and nickel, that you start to get little islands of stability in a sea of instability. And so heavier stuff doesn't last very long. It tends to break down into smaller things. It's a little like the game Chutes and Ladders that we played as a kid. You're climbing rolling the dice and climbing the ladder, but every now and then you get stuck and you slide down the chute to something smaller. So a lot of big elements reach a state where they become unstable and they break down and make smaller stuff. And they go back to the beginning and start forming new elements again. But it's tough to make big stuff, and you need a supernova and the kind of energy in a supernova to make anything bigger than about nickel.
So the relationship is the amount of energy required, and does energy relate to heat? So if you can simplify this a little bit for me.
Sure, absolutely. Here, this chart does it quite well. If you look, there is
that's what I was thinking of.
Core temperature. So in stars like our sun, you're talking about tens of millions of degrees. By the time you get into red giant stars, you're up to fractions of a billion degrees. Red supergiants, you're almost a billion degrees. Massive red supergiants, you're up at 3 billion degrees. And by the time you get into a supernova, you can see your orders of magnitude more hot. You've now jumped up 2 full orders of magnitude in the amount of energy that happens when a giant star collapses and then this supernova process takes over. It's a fundamentally different thing than the normal fusion that's happening in the regular series of stars. It's what they call a multiple neutron capture. You're basically breaking the atoms down into free neutrons, which now freely exchange with one another. And you create all kinds of big, massive elements, and the amount of energy given off is just staggering. And so the whole thing just explodes and casts the dust out into space that then goes through another cycle of making stars. And we're on the 3rd or 4th generation star with our sun. Did that answer your question?
So in simplifying it is, if it was simplify the explanation a little bit here, it does have to do with the amount of heat that is required to do this.
Heat is a huge part of it, but it's also density. It's how tightly are you cramming atoms together in the cores of these stars. Okay. So the bigger you are, the more gravitational crush you're feeling. So the temperature goes up,
Yeah.
the proximity of atoms to one another goes up. And so you start getting processes happening when you get them close and you get them hot and moving really fast. So.
Okay, thanks.
There's another question in the chat from Jonathan. Says, does the amount of heavier atomic minerals that have a half-life, such as uranium, indicate how long ago the last supernova event occurred prior to our solar system forming?
Uranium, it's beyond the chart, so I can't really pull up something to show it, but uranium has some relatively stable isotopes that last for hundreds of millions of years. So the uranium that we see was probably created in the supernova right before our solar system formed. So it's probably from that last major energy event that created the stuff from which we made our solar system. And it's just had long periods of time to decay, but some of it is still around. And the only reason we even see it in minerals is that you have processes like the ones that create minerals out of lithium, beryllium, boron. You have processes that refine them so consistently that they end up in the residua at the end in enough quantity that they can make minerals. And so it's just the refinement that goes on in plate tectonics and igneous processes that ends up allowing you to make uranium minerals from an extremely rare element like uranium. And we can go to the chart of abundances right here, and you can see uranium. Let's see if we can find it on the chart. Way over on the right, you can see it's an extremely unusual mineral, unusual element. It's about as common as tungsten or cesium or molybdenum or bromine or germanium. So I mean, it's not a terribly common element. So you need to have an awful lot of geologic processes continually refining it and extracting it and purifying it to get it in concentrations where you actually make uranium minerals. Hopefully that answered his question. So do we have any other questions, or should I go on to the raffle?
This isn't a question, but I want to thank you for having this online because I live in Provincetown and couldn't make it to in-person meetings.
Yeah,
I so appreciate it.
There's been a lot of people who have requested that we do hybrid meetings, that we project them as well as have them in person. And we would love to do that. But unfortunately, the meeting room we use at Harvard does not have an internet connection sufficient to do that. And we haven't got anybody who's got a phone with a connection that we can use strong enough that's willing to pay the price of broadcasting to do that. So we just haven't found a way to do it, unfortunately. We would love to do it, but we have not found a way to do it.
Well, I'm glad I got to come to this one. That's for sure.
Well, I suspect the next couple of months are going to be virtual just because of the winter spike we're having. So you'll probably get a few meetings under your belt over the next couple of months.
Great. Thank you.
Okay, so last chance for questions before we go to the raffle. It sounds like Jonathan does not have a microphone, so I'm going to have to do this, and I'll send him the information at the end, or I'll request people to send him the information at the end so that he can mail the samples out to the people who won. I don't know if anyone can see my phone. I'm going to type in, I have 44 names, so I'm going to type in 44 as the number. Okay, back. Oops. Delete 44. So we got 44 names on my list. And I'm going to generate a random number. Number 6 looks like Diane Beckman is our first winner.
Hi.
Which of the 5 would you like?
Can you hear me?
I can hear you.
Oh, awesome. You made it tough because there's a lot of nice things here.
Jonathan made it tough. Thank him for the selection.
Really don't know how to choose. I think I'll just make it simple and go with the clinozoisite from Vermont.
Clinozoisite. Okay, number 3. I will put you down for number 3.
Thank
okay.
you.
Next random number is 34, which is Don Ernst. Don, are you still with us? Does anybody see Don on the list?
I think I saw that he left at some point.
Okay, I'll give him about 10 seconds, then I'll pick another number.
Yeah, he's not on the list.
He's not on the list. Okay, so he must have left. Next is 43. We got Herbert of Andrea and Herbert. Is Herbert here? Anybody see if Andrea and Herbert are still on the list?
They're still on the list, Scott.
Can anybody see if they're trying to get to us in the chat, if they're having trouble communicating?
I checked and I don't see them there.
Okay, I'll give them the usual 10 seconds timing, and then I'll pick another number. Okay, next number is 13, which is Jim Armstrong.
We have a winner.
We have a winner.
I'll take number 2.
Number 2, the Florictorite. Okay. Next, we have number 1, which is me. Yay! Just to show you the camera, I actually number 1 showed up. I'm going to take the
This raffle is rigged.
Rigged, I tell you. I'm going to take the Roncari Amethyst, number 5.
Pass on that. Yeah, the L-bank might be.
Number 20 is Sivan of Ness and Sivan. Is Sivan here?
Yeah.
Oh, yeah.
What do you want?
4.
4.
Number 4.
We'll take 4.
All right. Okay. Sivan gets number 4. So let's see. We got 1, 2, 3. So number 1 is left. So the agate. We're going to see who gets the agate. Number 5. That's Dave H. Is Dave H. still with us?
Yes, I am, Scott.
Are you interested in the agate?
I'll take it.
You'll take it. Okay. For those of you who don't remember the details, you need to send Jonathan an email with your mailing address so that he can get these winning minerals to you. I don't know if he can.
Does he know which mineral went with which person?
I'm going to send him a list, but you should all send him an email saying, I won, and describe the specimen. Don't just give him a number because he'll get confused. He needs to know, I won the agate, I won the Florictorite, I won the Clinozoisite. So send an email to Jonathan. I don't know if he can put, because he's having some speaker problems, I don't know if he can put his email in the chat so that people can find it. Otherwise, it's in the
Jonathan, I can read the chat.
He has put it in the chat.
He has put it in the chat. Okay, so those 5 people who just want a specimen, you need to send an email to Jonathan with your mailing address and which mineral you actually won. Not the number, but the actual description, the mineral type, so that he knows which one is yours. And if there's nothing else, I think that's going to be the end of the meeting. Is there anything anyone else wants to toss in before we call it a day?
I want to say that I really appreciate you taking the time to do such a thorough and interesting meeting. It was terrific.
Well, I was hoping I wouldn't lose anybody.
Thank you, Scott. Very good.
Yeah.
Thank you, Scott.
Thank you.
Very nice talk.
It was great. Really great.
Glad you enjoyed it. Okay, well, I'm going to turn off the recording. Thank you all. Have a good night.
Good night.
Night. Thanks.
Everyone.